Welcome to confidence intervals. So let's say we're investigating the heights of 16-year-old American males. Say we also know that the population mean height is 65.3 inches with a standard deviation of 4.2 inches. Let's say we take a sample of 30 16-year-old American males. Will the mean height of the sample always be 65.3 inches? So basically that's like saying all of the 16-year-old males in the world have an average of 65.3 inches. Now, we're just going to talk about 30, let's say 30 of my students as a sample. Do you expect that my 30 kids are going to have a average height of 65.3 inches? So the answer is no. I mean, it could happen. Yes, there is a possibility that your sample will have a mean of 65.3, but it's not really likely because the population average includes everyone. So that 65.3 is the balanced out height. Now, if you're talking about the sample, what if you happen to choose the really tall people in the sample? And then your sample average will be higher than 65.3 because your sample didn't include the people who happen to be shorter than 65.3 inches. Do you get what I mean? I mean, it's not that everyone is 65.3 inches. There's a standard deviation going on here. So we're going to say not likely, all right? Just because you have a population average of 65.3 doesn't mean that that's going to be your sample average as well. So the next part of the question asks, what do you think will happen if we take a lot of different samples? So basically right now we have one sample of 30 16-year-old American males. Then you can take another sample of another 30 kids, and then another sample of another 30 kids. And once you keep taking all these samples, eventually you're going to have every single combination of samples of 30 possible. And you'll see that out of all of these samples, if you were to take the averages of all of these sample averages, you'll actually get back to the population average. Just an interesting fact. So now let's go on to our definitions. We have parameters and we have statistics. Now a parameter is a number that is calculated from a population data. P parameter for population. So here we're talking about mu for your population mean, or we're talking about your sigma, lowercase sigma, for your standard deviation for the population. Now, statistic is a number that is calculated from the sample data. So S for sample and statistic, and is used to estimate the population data. So a statistic would be considered X bar because it is a sample average, or your S sub X, the sample standard deviation. So just keep in mind, if you see mu, we're talking about the population average. That is your parameter. If you see X bar, we're talking about a statistic. Now, we use the statistics, right? Your data from the sample to estimate what will happen in the population. So now we have a sample proportion. It is the ratio of x over n, where x is the number of times an event occurs, in a sample size of n. So for example, let's say we're talking about who does homework in the class. And this particular time, let's say that 22 out of 26 students do the homework. This would be your sample proportion. You can also express it as a decimal. And of course, the numbers I chose are not nice, but that would be about 0.85. So your sample proportions will either be a fraction or a decimal. And it's actually called p hat. That is this p with like, kind of looks like a hat is on top of it. So we call it p hat. Now, keep in mind that this is a sample proportion, right? So this 0.85 is just the percentage of the times that, my students in first period do the homework. However, if you wanted to make it the population proportion, I would take it out of all of my students and find that. So when you're talking about a population proportion, that becomes just P. P hat is only for sample. Now, your sample mean is the average of the sample found by adding all of the sample data and dividing by n, where n is the sample size. We know how to find averages. So just keep in mind that sample mean would be x bar, whereas the actual mean for the population will be mu. Now, last thing to go over is a simulation. It is a computer-generated model based on a real-life event. So usually what happens is we take a sample and we gather data from it, and then we put it into a computer, and it makes like 1,000 of these simulations based on it, and comes up with a simulation average and a simulation standard deviation. And the thing is, while it might be hard for us to do all of these different trials, the computer can do all these different trials quite easily from our one original sample. So the simulation runs this so many times that they get more accurate answers. So when you see a computer simulation in a problem, you're always going to use the simulation results because they will be more accurate. And that's important because sometimes problems give you the results that a person got and also the results from a simulation, and you have to know you need to use the simulation results. Okay, now we're actually going to talk about confidence intervals. What's the video all about? So a confidence interval is the range or interval of values found by adding and subtracting the margin of error to and from the statistic with the goal of trying to capture the true population characteristic. What does that mean? So let's take the example of when you take tests in my class. After my first period tests, I can look at the results and then make a prediction on how my other periods are going to do on the test, right? So let's say I graded first period's test and the average of the test was an 85. That means it's safe to assume that my other two classes will have somewhere around an 85 average as well, unless something drastic happened in one of them that changed their test grades. But in general, if my first period does pretty good, then my other periods do pretty good because they get the same instruction. So just because my period 1 gets an 85 average doesn't mean that my other two periods are going to get the same exact 85 average, right? So what happens is we use the first period's results and we're going to come up with a range of values that my other periods might fall in between. So that range is called a confidence interval. It actually is a 95% confidence interval. We can say with 95% certainty that my other classes are going to get this within the same, they're going to get an average within that interval. So if you see confidence interval, if you see 95% confidence interval, it all means the same thing. A plausible interval is another word for it as well. The 95 comes from, if you remember, in the normal CDF lesson. 95% of the data falls within 2 standard deviations of the mean, which is what we're getting at here. So what happens is we have a margin of error, right? My first period average is not going to be the average for all the other classes, so we need some wiggle room to create this interval. That wiggle room is called your margin of error. You're going to start at the average and go up by the margin of error, and you're going to start at the average and go down by the margin of error. In order to find the margin of error, you need to do 2 times the standard deviation. You're going to see in the video that a lot of the time I write it as 2SD, 2 times the standard deviation, because I don't want to write it all out. Now you have 2 different options here. So the first option is when we're talking about test averages, right? That's this guy. Because you're talking about the average grades, you're going to be using X bar. Now, the one on the right is slightly different. A good example of that is what proportion of people pass the test. Now, hopefully we all pass the test, so let's say the proportion of people passing my test was 95. 95% of the people passed the test. That means p hat would be 0.95 from period 1, and I would add and subtract the margin of error to figure out what percentage of people are going to pass the test in my other classes. So keep in mind that X bar is for averages, p hat is for proportions. And let's try some examples. You can tell right off the bat, because I have decimals, I'm not talking about X bar. We're not talking about averages, we are talking about proportions, which means we're talking about p hat. So the margin of error and the sample proportions are given for each of the following. Determine the confidence interval in each case. So you have 0.25 plus 0.2, 0.25 minus 0.2. That's going to give you 0.23 and 0.27. Now, there are several ways to write your answer. One of them is, and probably the easiest one I'm going to be using, is 0.23 to 0.27. The other way of writing it is using interval notation. That's going to be 0.23, comma 0.27. And then the last way of writing it is going to be that 0.23 is less than p is less than 0.27. Now notice how this is p hat, and this is your margin of error. We use p hat and the margin of error to guess where the population proportion is going to lie. So this is your sample, whereas this is your population proportion. And that's why I'm going from p hat to just a basic p. We're estimating where the true population proportion is going to be in. So all you have to do is break it down the same exact way for the other ones. You're going to have 0.67 plus 0.17, 0.67 minus 0.17. You do not have to write this out. If you don't want to, you can go straight to writing that the answer is going to be 0.50 to 0.84. Why don't you try C and D? Okay, now hopefully you got the same answer as me. In number 2, you'll see something different with the numbers right away. There are no decimals, right? We're talking about larger numbers. Now that means we're talking about sample means. We're talking about X bar, plus or minus your margin of error. So I'm going to have 56 plus 3, 56 minus 3, and that's going to give me 59 and 53. So one way to write the answer is 0.23. Oh, sorry, I'm looking up above on my paper. That's going to give me an answer of 53 to 59. Another way to write that answer with the interval notation would be 53, comma, 59. And then the last way to write it is 53 is less than mu is less than 59. Now, this time we went from our sample average to estimate the population average. So based on the sample average and the margin of error, we can be 95% confident that our population average, when you include everyone, is going to be between 53 and 59. Why don't you try the other 3 problems? All right, hopefully we got the same answers. Now, you'll notice that for all of them, I'm using this to that. There is a specific reason for it. Now, you are free to write them any way you want. However, in the assignment, you're specifically going to have to write it out like this. However, please be careful of writing it this way. There's nothing wrong with it. However, you have to know, are you talking about a proportion or are you talking about the average? Because if you mix it up, if you're talking about an average but you use p, you're going to lose a point. If you're talking about a proportion but you use mu, you're also going to lose a point. So it's easier to go with this to this, and then on the regions, you're not going to lose a point because you didn't include the notation in the first place. Now let's go on to the steps to creating a confidence interval for X bar or P hat. So you'll notice in the last example, we were given everything to us. We had P hat or X bar, we had the margin of error. Now we're going to be doing problems where they might not give you X bar or P hat, and you'll have to find the average or the proportion on your own. And then they're not even going to give you the margin of error. They're going to be giving you the standard deviation. So you're going to have to know, take the standard deviation, multiply it by 2 to get the margin of error. And then you're going to have to do what we just did on creating the confidence interval. Most of these problems are going to ask you to take it a step further. They're going to use your confidence interval, and then they're going to see if the true proportion or the true mean is contained in the interval you created. So if it's contained in the interval, then it's likely to happen. If it's not contained in the interval, then it's unlikely to happen. Let's try an example. So we have a newspaper in California took a random sample of 500 registered voters from Los Angeles and found that 300 of them favored a certain candidate for the mayor of the city. The standard deviation was 0.12. The newspaper also claims that the true proportion of voters who favor that candidate is 45%. Using these results, explain what statistical evidence supports the newspaper's claim. So, first of all, saw the word proportion, so I know that we're dealing with p hat. That means, oops, It means that your first step is going to be figuring out what p hat even is. Now, you do have to read carefully, and you have to distinguish between population and sample. Now, it says we took a sample of 500. Of that sample, 300 of them favor this candidate. So p hat is the 300 out of the 500 people. Now, usually p hat will be represented as a decimal, which is going to be 0.6. That means 60% of them favored the candidate. So you have p hat, and now you need your margin of error, which they do not say in this problem, but we know that margin of error is twice the standard deviation, and they gave us the standard deviation in this problem, which was 0.12. From there, you can figure out your confidence interval. So your confidence interval, or CI in this case, because I don't want to write it all out, is your population proportion, 0.6, plus or minus the margin of error, which is 2 times the standard deviation. Based on that before, 0.6 minus 0.24 is going to be 0.36, and 0.6 plus 0.24 is going to be 0.84. So we can say we are 95% confident that the true proportion of voters who favor this candidate will lie between 36 and 84%. However, this newspaper is claiming that it is 45%. Or in this case, if you want to go back to proportion, you can say 0.45. So does our evidence support or reject the newspaper's claim? Now, I would say that it supports it because 0.45 falls between 0.36 and 0.84. Or not within, rather between. So it did ask you to explain, and a proper explanation would be this. The claim is supported since it falls within the confidence interval. You could write it a different way, but overall it has some of the same gist as this sentence. We're going to do 2 more examples that were from Regions questions. Now, in this one, a radio station claims to its advertisers that the mean number of minutes commuters listen to the station is 30. The station conducted a survey of 500 of their listeners who commute, and the sample statistics are shown below. So in this box here, you have the results from the survey. Using those results, a simulation was run 1,000 times. The results of the simulation appear below. So which one do you think has better results? Do you think that the one survey has more accurate results, or the simulation done 1,000 times has more accurate results? I would say the one done 1,000 times is more accurate than the one done once. So again, because we have a simulation, we are going to use these results. I don't even care what happened up here. So based on the simulation results, again, it's just backing up that you should be using what happened from the simulation. Is the claim that the commuters listen to the station on average 30 minutes plausible? Explain your response including an interval containing the middle 95% of the data. Again, middle 95%, we're talking about a confidence interval here. And they want you to round your answer to the nearest hundredth. Now, in order to find your confidence interval, you need the average and you need the margin of error. Your average is your mean. This is your bar going on. So I have that my x bar is 29.101, and my margin of error is 2 times the standard deviation. My standard deviation is 0.934. So that gives me a margin of error of 1.868. Now to find your confidence interval, I'm going to take the average, 29.101. I'm going to add and then also subtract the standard deviation, not standard deviation, the margin of error, twice the standard deviation. When I subtract the margin of error, sorry, I'm going to get 27.233. When I add the margin of error, I'm going to get 30.969. Now the problem did tell you to round to the nearest hundredth. Now that you're finally done, you can round to 27.23 to 30.97. Now the problem asked, is it plausible that they listened to the station for an average of 30 minutes? And look at your confidence interval. Does 30 minutes fall within that range? Yeah, because 30 minutes is more than 27 and less than 30.97. So we're going to say yes, because 30 falls within the confidence interval of 27.3 to 30.97. Now, notice how in this one I actually included the numbers of the confidence interval. That's because the question is saying explain your response, including an interval, right? And then even told us how to round it. So because they're telling me to put in my response, I actually wrote it out. Okay, last one. A group of students was trying to determine the proportion of candies in a bag that are blue. The company claims that 24% of candies in the bag are blue. A simulation was run 100 times with a sample size of 50 based on the premise that 24% of the candies are blue. The approximately normal results of the simulation are shown in the dot plot below. So basically each and every dot represents one simulation, because not every single bag is going to have exactly 24% of the candies being blue. So when they ran the simulation the first time, there was one simulation that had 10% of the candies being blue. There were 2 simulations. Well, I don't know what that number is, so I shouldn't choose it. Let's see here. There were 10, because there's 10 dots. 10 simulations in where 30% of the candies were blue. So all these dots just represent a simulation, and if you were to add all the dots up together, you would get 100 dots, because the simulation was run 100 times. Anyway, it says the simulation results, which is what you want to pay attention to, in a mean of 0.254, that is my p hat, because it was based on the sample, and a standard deviation of 0.06. This is going to be your sample standard deviation based on the simulation. What is a plausible interval containing the middle 95% of the data? So they want a confidence interval. You're going to take your p hat and you're going to add and subtract your margin of error. Now I know that my p hat is equal to 0.254. I do not know the margin of error, but I know that it is twice the standard deviation, So 2 times my standard deviation of 0.06, which is 0.12. So my confidence interval is going to be 0.254. Oh, that is so bad. I'm going to add and subtract the margin of error of 0.12. When you subtract 0.12 from 0.254, you're going to end up with 0.134. When you add 0.12 to 0.254, you're going to get 0.374. Now again, another way to express a confidence interval is with interval notation using the parentheses. Now, if worse comes to worse, and you forget all the math between this, we're talking about an interval that contains 95% of the data, right? So you can go one by one through all this and see which one has about 95% of the data. So let me erase everything. Let's go one by one. Let's work from the bottom up. Choice 4, we're talking about 0.254. Let's see where that would be. That would be, I don't know, here to 0.37. Let's say that's here. This guy right here, this interval, does that have 95% of the data? 95% of all the dots. I would say, no, it doesn't. It looks like half of the amount of dots. So it can't be choice 4. Now, let's get rid of this and look at the next interval. Negative 0.4, which isn't even on the screen. So I don't know, I guess put the negative over here, I guess, just because, I have nowhere else to go. So we're going from negative to positive 0.5. And 0.5 is not on this chart either, so let's say that 0.5 is over here. So we're talking about this very large interval. Is that 95% of the data? And no, it's not. It's like more, it contains 100% of the data, not 95. That one is too large. Let's talk about choice 1, 0.194, which would probably be about here, to 0.314, maybe here. Even this doesn't have 95% of all of the dots. It has a lot of the dots, but not 95% of it. So choice 1 isn't really good either. Now let's try the last one. 0.134, maybe that's about here, to 0.374. Let's say it's here. Now this interval contains not all of the dots, not 100%, but most of them. So that's fair to say it contains almost all the dots, 95% of the dots. So you can do the problem visually. However, please be careful. You don't want to do it like this because sometimes the answer choices are so close where, yes, you might get 2 answers that are possible, so you can eliminate it down to 2 choices, but it is possible that you'll choose the wrong one based on your judgment of just looking at the graph. You're going to want to use the formulas based on the rest of the video to get the true mathematical answer. That way there's no room for error. So just to recap, based on our statistics, right, the sample average and the sample proportion and the sample standard deviation, we can create a confidence interval to assume where the actual population parameters are going to lie, where the population average is, where the population proportion is. And that is going to be 95% confident that is going to lie within that range. Then from there, you get that by either doing p hat plus or minus your margin of error if you're talking about proportions, or you do your x bar plus or minus the margin of error if you're talking about your averages. The math is the same. The only thing that changes is the notation, which we talked about how you can avoid. Keep in mind that your margin of error is equal to 2 times your standard deviation. And then last but not least, if they give you a computer simulation, always use the simulation results. And that's all for this video.